Good morning, my dear students. Welcome to my physics class. Our today's topic is the variation of weight in a lift, weightlessness. At first, we will learn what is weight. Already we know it. What is weight? The force by which Earth attracts an object towards its center is called weight. That is, weight is one kind of force. The force which applied by the Earth on the object, and it is denoted by W. Its SI unit is Newton, and we know weight W is equal to mg. That is, weight is one kind of force applied by the Earth on the object towards the center of the Earth. So weight is the force on the object applied by the Earth. And also you know weight W is equal to mass into acceleration due to gravity, that is W is equal to mg. And we know m is constant for a fixed body. So weight of a fixed body depends on acceleration due to gravity g. That is, weight depends on g. The value of g at a certain place on the Earth's surface is constant. We know g varies from place to place. From one place to another place, the value of g will be different. But for a certain place, the value of g is constant. As the value of g is constant for a certain place, so at a fixed point or at a particular place, the weight of a body is constant. So at a certain place, our weight is fixed. That is, if we consider at Pabna our weight is fixed. But if we move from Pabna to Dhaka, our weight will be different. But at a certain place, our weight is fixed, because at a certain place, acceleration due to gravity is constant. Though at a certain place our weight is fixed, we may feel the variation of our weight. We know our weight is fixed at a certain place, but we may feel the variation of our weight. What is the reason of variation of our weight at a certain place? How do we feel our weight? We will know how do we feel our weight. We know to every action there is an equal and opposite reaction. If we apply force on a body, the body will also apply force in opposite direction. This is known as to every action there is an equal and opposite reaction. When we stand on a surface, we apply force F on the surface equal to our weight. That is, F is equal to W is equal to mg. Here m is the mass of this man, and he is standing on a surface. At the standing position, he is applying force on the surface, and this force is equal to the weight F is equal to mg. Here mg is the weight of this man, and he is applying force on this surface. F is equal to mg. And we know to every action there is an equal and opposite reaction. As the man is applying force on this surface, and this force is F is equal to mg, so the surface will apply force on this man, and this force is known as reaction force, and this reaction force is equal to F. We know to every action there is an equal and opposite reaction. So applied force F is equal to mg. This is the weight of this man. It is real weight. And the reaction force applied on this man is R is equal to F, and it is also mg. Therefore, the surface will also apply reaction force R is equal to F on us. If we stand on a surface, we will apply force equal to our weight mg. So the surface will also apply force on us, and this force is known as reaction force R. And reaction force R is equal to applied force F, and which is equal to our weight mg. So we can feel our real weight mg, that is, we feel this reaction force. When we apply force on a surface, the surface will also apply a force, and this reaction force is equal to the applied force mg. And we feel our real weight mg because we feel actually this reaction force, and this reaction force is mg, so we feel mg. So generally we feel our real weight because we apply the force equal to our weight, and the reaction force is also equal to our real weight. So normally we feel our real weight. Here reaction R is our apparent weight, and this reaction is apparent weight. Apparent weight may be different from our real weight. In this case, apparent weight is equal to our real weight. That is, we feel this reaction, and this reaction may be different from our real weight. When the lift is at rest, we apply force F on the floor of the lift equal to our weight mg. Inside the lift, we apply force on the floor of the lift, and this force is equal to our weight mg. So we feel our real weight R is equal to mg. That is, here applied force is mg and reaction force is also mg, and we feel this reaction force, and here reaction force is equal to mg. So we feel our real weight when the lift is at rest position. So when the lift is at rest position, we feel our real weight. But when the lift moves in upward direction with acceleration a, that is, in this case there is additional acceleration of the lift, the reaction force on us becomes R is equal to mg plus ma. Here the lift is moving in upward direction with acceleration a, so the reaction on us is mg plus ma. Here ma is added with mg. Our real weight is mg only, but as the lift is moving in upward direction with acceleration a, therefore the reaction force acts on us is mg plus ma now. So we feel mg plus ma force. So the apparent weight is mg plus ma. So we feel our apparent weight R is equal to mg plus ma, which is more than our real weight. We know our real weight is mg, but now the apparent weight is mg plus ma. This ma is added because this lift is now moving in upward direction with acceleration a. We feel our reaction force in upward direction, and here the lift is also moving in upward direction. So reaction force is mg plus ma, which is more than our real weight. So when the lift moves in upward direction with acceleration, then our apparent weight is more than the real weight. Therefore, inside the lift, when the lift start to move, we feel ourselves more weight. That is, we feel our weight more than our real weight inside the lift. When the lift start to move, that is, when the lift start to move, we feel our weight more than our real weight. But when the lift moves in upward direction with constant velocity, the reaction force on us becomes R is equal to mg only, because now there is no acceleration of the lift. Acceleration means the velocity or speed of the lift will be increased. Initially, the lift is at rest position. When the lift is start to move, then gradually its speed will be increased. So it will have a acceleration. But after some time, the lift will move with constant velocity, and when the lift moves with constant velocity v, then there is no acceleration, so there is no additional term here. So the reaction force on us is mg only, so we feel our real weight r is equal to mg. So when the lift is at rest position, we feel our real weight. When the lift moves with constant velocity, then we feel our real weight. But if the lift moves in upward direction with a acceleration, that is when the velocity of the lift is increased, then we feel the apparent weight, and the apparent weight in this case is more than the real weight. But when the lift moves in downward direction with acceleration a, the reaction force on us becomes r is equal to mg minus ma. Here reaction force is mg is in upward direction, but the lift is moving in downward direction with acceleration. So the net reaction on us is mg minus ma. So reaction force mg minus ma, this will be the apparent weight. The apparent weight is mg minus ma, and mg minus ma is less than mg, so we feel less weight when the lift moves in downward direction with acceleration a. That is, the lift, when the lift moves in downward direction with acceleration a, the apparent weight is less than our real weight. When the lift moves in downward direction with constant velocity, the reaction force on us becomes r is equal to mg. That is, in this case, the lift is moving in downward direction with constant velocity. That is, there is no acceleration in this case. If there is no acceleration of the lift, our apparent weight will be equal to the real weight. So there is no variation of weight when the lift moves with constant velocity. We will feel the different weight when there is acceleration of the weight and lift. So we feel our real weight r is equal to mg. When the lift moves in downward direction with acceleration g, in this case the acceleration a is equal to acceleration due to gravity g. The value of g is 9.8, and if the lift moves in downward direction with the acceleration 9.8 meter per second square, then here a is equal to g. So the reaction force on us becomes mg minus mg in this case. Here mg minus ma instead of ma, here mg. So mg minus mg is equal to 0. So reaction force on us is 0. If there is no reaction force on us, we will not feel any type of force. So we will feel ourselves weightless in this case. That means we cannot feel our weight, because we feel the reaction force only. As there is no reaction force, so we cannot feel our weight. In this case, our apparent weight is 0. When the cable of the lift tears, the lift falls freely in downward direction with acceleration g. This will happen if the cable of the lift tears in any way. Then the lift will move in downward direction freely with acceleration g, and then we will feel ourselves weightless. Thank you very much.